Session will be by Michal Derezinski.
Thank you. And thank you to the organizers of the workshop. I'm currently a postdoc at UC Berkeley, but most of this work I did at UC Santa Cruz with my collaborators Manfred Warmuth, who's here, and at UC Santa Cruz, and Daniel Su at Columbia University. So I'll be talking about unbiased estimates for linear regression via volume sampling. Okay, so let's start with a basic, just basic motivating example. We're all familiar with least squares regression. We get a bunch of points xi. Each of them has an associated real label yi. We would like to fit a line through it. For simplicity, for now, let's assume it's a one-dimensional example. So the least squares solution says, okay, let's minimize the total square loss. We get this green line that sort of fitting the data. Okay, so here's the twist. So let's say we have the input points xi, but the labels yi are unknown to us or hidden from us. So we can query for a point xi for the label to be revealed. So now the question is, how many labels do we need to query if that's expensive? How many labels do we need to query to get a meaningful approximation of the least squares solution? And what is the smallest number that can give us a meaningful answer? So it turns out, in this case, one label is enough. So what that means is, we query one point xi, we receive one label. Naturally, we're going to predict with the line that goes to that point. Right here, we assume there's no sort of bias term in the linear regression example, right? So the line goes to the origin through the point. And it turns out that we can show, if properly chosen xi, then this blue estimate from just one point is the loss of that estimate on the whole data set is within a factor of 2 of the loss of the optimum estimate based on all of the samples. So how do we choose that one point? Well, the natural intuition is to sort of pick a point that has high leverage, right? So it's far away from the origin, so it has big influence on the green solution. But if we choose it deterministically, we can run into trouble, outliers. So we want to sort of randomize, right? So here we're going to pick a particular distribution which samples one point proportionally to the xi squared. And it turns out, if we do that, that has some interesting properties. So in particular, if we look at the total loss of this blue estimate in expectation with respect to that sampling, keep in mind that the labels here are fixed. There's no randomness in the labels. So then the expected total loss is 2 times the loss of the best. And that is an exact identity. Also, it turns out that the expected value of the estimate itself, the blue estimate, is exactly equal to the green estimate, which means that we have an unbiased estimator of the least squares regression, just with sampling one point, with only ever observing one label. So naturally, we can ask, how does this generalize to more dimensions? Okay, so let's set up that problem. We've seen this kind of slide many times here. We have n points in d dimensions. So we have real labels yi. The labels are hidden from us. We put the points in a matrix X where the rows are the instances xi. And we want to minimize the total square loss over all n points. So we want to sample a bunch of points, a set of indices S, right? And then receive labels for those indices. So now, natural way to proceed, once we have the sample, we just solve the least squares problem for the subsample. So that can be written in a closed form as a pseudo-inverse of the submatrix X sub S.
So how do you know X sub S is a full form, right?
Sorry?
So how do you know that inverse exists there?
Well, the pseudo-inverse will exist.
But that inverse not necessarily.
That's true. So, I mean, yes. So we will actually be picking points in such a way that the X sub S is full rank. But good point, yes. If the X sub S was not full rank, then you can still write the pseudo-inverse part. Okay, so now I'm going to introduce volume sampling. So let's recall for dimension 1, we decided that it's reasonable to pick a single point with probability proportional to xi squared, right? So it turns out in d dimensions, it's natural to pick d points, a subset of d points, with probability proportional to the squared determinant of the submatrix, right? So there's this sort of analog here. And the intuition here is, in some sense, we want to pick a whole subset that has a high leverage, right? So that, and the determinant, the interpretation of that is that it's so the determinant squared is the volume, the squared volume of the spanned by the points, so the squared volume of the parallel pipette spanned by the d points, the vectors, or the rows xi. So it kind of spreads out the points. And of course, if we want to sample more than d points, this can be also naturally generalized to sets of arbitrary size at least d. And so this is the volume sampling distribution. For the size d, it first appeared in a paper by Deshpande, Rademacher, Van Pala, and Wang. And then the extension to larger than d appeared in Avron and Boutsides' paper. So there's this normalization here, the z, right? So we're sampling proportionally to the determinant of x sub s transpose x sub s. What is the normalization? It turns out it's easy to derive using the sort of standard Cauchy-Binet formula, which basically tells you what is the sum over all determinants of those submatrices. And that turns out to be a factor times the determinant of the x transpose x matrix. Okay, so how does the result for one-dimensional case generalize to d dimensions? So we showed that for if we volume sample a d-element set S in the regression problem discussed earlier, right? So we get d points, we receive the d labels, we compute w star of S. The expected loss, total loss on the whole data set of that estimator will be exactly equal to d plus 1 times the loss of the best. And this is an exact formula whenever x is in general position, meaning that essentially all the subsets of points are non-degenerate. This is sort of a minor assumption, and if it doesn't hold, then instead of the exact equality, you get an upper bound, which is still good. And on top of it, the expectation of the estimator itself is again equal to the optimum estimator. So we essentially recover the same statement as before in one-dimensional case, except now we have to sample d points, and the factor sort of grows with the dimension. But again, the sampling distribution does not depend on the labels, and it does not depend on any noise model of the result does not depend on any noise model of the vector y, right? So it's for fixed y's. Yes?
Just like to be 100% clear, when you say expected loss, you just mean like the sum of squared errors. So there's no randomness in either the labels or the data.
Exactly. So it's a fixed matrix X, fixed vector Y. You're sampling subsets, and the expectation is with respect to just the sampling.
Okay.
What is that expectation when you choose 1 point? It's 2 if you sample with the norm or norm squared.
Exactly.
What if you do uniform or leverage or something else? Is it immediate to get? 1 point.
In one dimension?
Yeah, 1 point.
If it's, well, in 1 point, volume sampling is leverage score sampling. It's the same thing for 1 point because it's just the norm squared. That's what it is, right? So it's the same thing. If it's uniform, then well, then I guess you don't get it. I don't know that you get a formula. Or does that answer your question?
But the thing you're sampling is not the. Maybe I missed. I thought it was a row norm of A or whatever the letter you used for the matrix was in 1 dimension. So it's not the leverage; it's a row norm. Or did you put it in a orthogonal position?
Well, let's see. What is going to be the leverage score in 1 dimension, right? The effect of the so I mean.
And the k equals 1. That are equals
Why
1
you
squared.
normalize the vector to have unit norm, and then the leverage scores out of the elements of the normalized vector.
Right. So I mean, So basically, it's the same as if you sampled according to the square. So in that case, it's just...
So in that case, the matrix would be a vector. So I guess you're not rectangular with k equals 1.
Yeah.
So I guess the question would make sense if you're rectangular with k equals 1. Let's take it offline, because it...
Sure. Yeah, but I mean...
That's the case I was thinking.
Okay, so now we get to... So, of course, since we're doing sampling for linear regression, I have to ask, what about IID leverage score sampling? How does this compare? How does this fit? So, of course, that is used for this very task. We've seen many times here in this workshop leverage score sampling being used. So what happens? So this is IID sampling. So we define a weight for each point, so it turns out there's a very deep connection between leverage score sampling and volume sampling, and specifically, what it says here is that the leverage scores are marginals of volume sampling, which means that if I sample a set according to volume sampling, I can ask what is the probability of a particular row being in that set. And that probability exactly is the leverage score. So the way I think of it is this is another sort of argument why leverage score sampling is natural, right? Because it is actually, in particular in least squares setting, the way I think of it is you would like to do volume sampling, but maybe you want to do IID. So what's the natural thing to do? You go sample according to the marginals. So that's the connection. But of course, there's a trade-off here if you go to IID sampling. One is you run into the coupon collector problem, which is that you need to desample d log d samples to get sort of meaningful guarantees in general. The other one is that the estimators you get, at least for least squares, are biased.
By IID you mean independent, right?
Yes.
Sorry?
By IID you mean independent.
Independent, identically distributed.
No, I mean like they're not. I mean when you choose xi is not with the same probability as xi prime, right?
I mean, if you do IID sampling, right, you sample the first point according to leverage score distribution, then you sample the second point from the same distribution, and so forth.
Repetition. Okay.
Yes. So the first, right. So you want to sample a set, right? So how do you sample a set? You sample one point at a time, IID. Right, that's what I mean.
Yeah.
Okay, so volume sampling sort of takes care of both of those issues. And to show that this actually shows up in practice, just briefly, let's look at a few experiments. This are a bunch of benchmark linear regression data sets. So we're comparing basically X here is the subset size, right? So if our budget is this subset size, what do we get? What total loss do we get from the estimator? And we can see that if our budget is very restrictive, the subset size has to be small, then volume sampling works much better because, and you can clearly see the coupon collector problem appearing in some cases here. Right.
When you're doing leverage score sampling, are you reweighting the rows or?
Sorry?
When you're doing leverage score sampling, you're reweighting the rows to compensate for the leverage scores?
I mean, so I'm computing the leverage scores for every point, right, according to the formula that was there, and then sampling one point at a time according to that distribution.
But you're just using the rows and the right-hand side without changing them, without reweighting based on that.
Oh, am I reweighting the rows to get the estimate?
So you can reweight the rows on the right-hand side and then compute then solve the regression.
Yes. So in this case, I did reweight the. I basically did what you would normally do for leverage score sampling, right? So I would sample with this probability and then rescale the instances, right? For volume sampling, in this case, you don't need to rescale instances. Okay, so why should we be interested in volume sampling? So like I said, you have some new loss bounds which avoid coupon collector problem. Now, it's kind of curious that you get exact expectation formula there. And if you look at it more carefully, it turns out there's a whole family of matrix identities related to volume sampling that show up there. Yes?
So if you, for the fixed budget, if you go and find the largest item, the leverage scores, and just use those, no sampling, deterministically set the height. Just curious, how does that perform, you know?
And you're asking for leverage scores, not for volume, right?
Yeah. Instead of D log, you just, you don't have that. It's not random sampling anymore. It's pretty much.
There's already a counterexample in one dimension. If you pick the longest weight vector, it doesn't work.
Right. So
It's a factor of n.
So if you do deterministic sampling, right? In this setting, at least, when y is fixed and hidden from you, you can have adversarial vectors y that kind of are problematic. Okay. So also we have this new kind of unbiased estimators, which are sort of useful in various settings. For example, distributed settings when we want to combine them via averaging and improve the performance of the estimators. And also, I mean, volume sampling seems like a sort of complicated joint distribution, but it has a number of very nice properties, nice sort of closure properties, which, for example, means that you can easily sort of downsample or add samples to a set in volume sampling, preserving this sort of family of distributions, which significantly helps with the analysis. So let me actually talk about that briefly. So volume sampling is closed under subsampling. So what does that mean? Okay, so here's the following procedure. So we define volume sampling for any fixed size S, right? So we can, let's say we sample first sets of size T, larger than S, and then we get subset T, we construct a submatrix X sub T, we volume sample from that of size smaller s. So now we get a set S, and it turns out that S is distributed exactly according to volume sampling from the full set, from the full matrix. And that will come in handy. Okay, so let's look more closely at those unbiased estimators and matrix formulas that pop up. So it turns out volume sampling is very closely connected to this matrix pseudoinverse. So to kind of understand the setup here, so we have a tall matrix X, and by D, the rows are what we're sampling. We use the selection matrix IS to basically construct matrix ISX, which zeroes out everything that we didn't sample, right? So we have the same shape of matrix X, but everything else is zeroed out. And then we will look at this ISX plus matrix, which is the pseudo-inverse of ISX, and think of it as an estimator of the full pseudo-inverse of X. It turns out this is an unbiased estimator. So the expectation of this matrix estimator ISX plus is equal to X pseudo-inverse entry-wise, right? So, and on top of that, we can actually compute a matrix variance of that pseudo-inverse estimator. So here, this is sort of one notion of matrix variance one can consider. We basically square the estimator matrix and then subtract the square of the mean. And we get an exact formula, which has this factor here, which decays with the subset size, which makes sense. The variance should go down. And this, I will not talk much about this, but this has interesting implication in sort of experimental design and also in linear regression. There have been a number of papers that sort of used a variance of this formula. But in particular, the unbiasedness of this estimator immediately implies the unbiasedness of the least squares estimator, right? We can just multiply this ISX plus matrix with a vector y. So just to give you a sense of kind of the proofs that we have here, how do we go about showing this, for example, this unbiasedness property for the pseudo-inverse matrix? So let's say that we want to show the expectation formula for the formula f. So basically we want to show that under, say, volume sampling, expectation of f of s, which assigns some formula to any subset s, is equal to the value of f on the whole data set. So we will use the fact that volume sampling is closed under subsampling, which means that if say we show this formula for sampling of size s, then we can just sample to size s and then sample down to size s minus 1, and then just show that the conditional expectation is preserved, and then by induction the result follows, right? So that's, I mean, I'm kind of going over this quickly, but that's essentially the idea. The closure under subsampling is very useful for these kinds of proofs. And in fact, after that, the proof of the pseudo-inverse expectation formula is sort of 2 lines.
I'm sorry, how does it follow from Sherman-Morrison? Again, you need invertible matrices for Sherman-Morrison, right?
Sorry?
You need invertible matrices to apply Sherman-Morrison formula.
Yes, so you start, so I mean,
You cannot assume that all your submatrices are invertible, can you?
that's right, and in fact, we don't need to assume that this
But
formula
you say
holds without.
Sherman-Morrison, that-
Yes, so, okay, so what does volume sampling do? It samples a subset proportionally to the probability of, the probability is the determinant of the appropriate submatrix. So if the subset is rank deficient, then the probability is 0.
But
So
I see.
so you'll never sample it. So basically,
You have one over, right?
sorry?
Don't you have one over? No, you have
The determinant of excess transpose excess divided by normalization. So as long as the whole matrix is full rank, that's what I'm assuming. I guess I didn't say that. The full matrices has to be full rank. Or, I mean, that can be fixed also. But for now, let's say the full matrix is full rank. But we will never actually get to a subset that's not full rank. So that issue never arises. I mean, of course, you have to be careful when you write sort of the inverses.
It's really those probabilities of volume sampling that save you, because those probabilities recognize rank.
That's right, exactly. That's right. Yes, so why are we interested in these unbiased estimators? So like I said, if you have an unbiased estimator, you can sort of boost its performance by sampling several independent copies of it and averaging. And in fact, in this setup, you can just immediately see that if we have an estimator that has an expected loss bound and it's unbiased, then the average of k of those estimators will have an expected loss bound that's a factor of k better. So that's kind of useful, and that exactly occurs in the case of volume sampling. And it has sort of interesting motivations in ensemble methods, distributed optimization, and others. So there's an interesting open problem that arises here. Basically, how do we get an epsilon sort of relative error approximation with the smallest number of samples? We made some progress on this, but still, we conjecture that the d over epsilon unbiased estimator is possible.
I think it's already, you can prove it.
Oh, really?
Yeah. So you follow essentially from why volume sampling with d over epsilon rows gives you column selection.
Is it unbiased?
Sorry?
Is it unbiased?
Yeah.
The over epsilon is known.
Yeah, you get unbiased.
If you do what again? You sample d over.
You basically prove a stronger identity that's true, which requires majorization of you prove that this r plus 1 symmetric polynomial over the r symmetric polynomial, which is exactly what would show up here, would be is sure convex.
But what is the sampling you do? You just do d over epsilon volume sampling?
You just do d over epsilon volume sampling.
That's interesting because I have lower bounds for that.
Yeah, I don't think
So maybe we're using slightly different notion, but let's take it offline. But that sounds interesting, definitely. So like I said, there's a bias estimator that's d over epsilon, but the best unbiased estimator is essentially d log d plus d over epsilon. So there's a gap.
I thought your previous slide was basically saying if you average together, I thought it was going to be that if you average together 1 over epsilon volume samples, this would give this. Why does it not?
Right, it does. So that gives you is d squared over epsilon, just because the factor. The result that we had.
D plus 1 already.
Right. So the result that we had was for exactly size d volume sampling.
Oh, I got
And the thing is, you would like to sample a little bit more to get down to a constant factor, and then you can do averaging to boost that by 1 over epsilon copies. So there's, yeah.
So you get exactly the same as leverage score sampling. D log d plus d over epsilon is exactly what leverage score sampling.
That's right. That's yeah, exactly. But you make, so I'll talk, I mean, if I get a chance, I'll talk about it. But you essentially can correct the bias of leverage score sampling. Okay, so let's talk about algorithms. So again, we come back to the fact that volume sampling is closed under subsampling, and that immediately leads to a natural algorithm where, okay, we start with a full data set, and then we're just going to downsample by 1 point at a time. So we downsample by 1 to n minus 1, and then we downsample by another 1. So each time we just have to throw out 1 point, and we just have to figure out what is the conditional probability at each time. Turns out we can update the conditional probability somewhat efficiently in sort of linear time with the data set, but that still leads to the quadratic dependence on n because we have to throw out a lot of points. So, but actually this can be improved, and so I'll not get into the details, but basically you can do rejection sampling to avoid computing the whole conditional probability, and that works remarkably well, so it reduces the runtime to ND squared, which is sort of somewhat satisfying because essentially the first step of this algorithm is just computing x transpose x. And if you do that exactly, that's already ND squared. So volume sampling is the only constant factor on top of it here. Okay, so here's an interesting extension of volume sampling, which sort of connects back to a lot of the things that appeared at this workshop. So we want to somehow regularize volume sampling in such a way that we can get away from the dependence on the dimension D. In fact, in volume sampling, it's particularly sort of important because you cannot sample sets smaller than D unless you regularize, at least in this framework. So instead of using the simple determinant, which would be 0 for sets less than D, you use the determinant plus some regularization. And it turns out you can recover very sort of good sampling guarantees for ridge regression in terms of the statistical dimension. So this is the standard statistical dimension for ridge regression. It will be much smaller than the dimension D whenever sort of maybe the data is approximately low rank or so forth. And you will only need to sample D lambda, the statistical dimension, many points with volume sampling to get error bounds, which I will not get into, but they're provable error bounds here. Okay, so I mentioned leveraged volume sampling briefly, and it's sort of interesting from the context of from the algorithmic perspective. And so here's the basic idea. It turns out if you sample enough IID leveraged score samples, then with high probability, that sample contains a smaller volume sample, which means that if you sample enough points, then you can probably select a subset that's well spread out. But in fact, we can do more than that. We can actually say, if I sample enough leveraged score samples, I can sort of transform that sample using rejection sampling in such a way where it's exactly a volume sample. And then
it's all the unbiasedness properties with respect to it.
Exactly. So all of the unbiasedness properties come through. And again, we could use the downsampling, the closure property to say that now we can downsample to any small size, such as D. And so the runtime of this procedure, so this is nice. If we had leveraged scores, this is immediately, there's no dependence on N, it's just polynomial in D. And of course, computing leveraged scores can be made quite efficient. So essentially, this gives us an NNZ of X time plus poly D time for volume sampling. And one way to think about it is that this procedure basically corrects the bias, the bias in the least square solution for the leveraged score sampling. Right. So okay. So we talked about a bunch of algorithms. So let's put this sort of in context, in practical context. So there's an example benchmark data set, libSVM data set. How efficient can volume sampling be? So as a comparison, we look at how long does it take to compute leveraged scores. So all of this, including leveraged scores, so sort of should be comparable running times. So that's pretty fast, right? So it's not such a large data set, right? So we would like to make volume sampling at least close to it, right? It's clearly going to be at least this much because it's a more complex distribution. Computing leveraged scores is just a pre-processing step for it. So the first algorithm was only last year, the first polynomial time algorithm. And it doesn't quite get efficient runtime in this case. Although this is only a rough estimate, I wasn't patient enough to run it. So afterwards, and this was only last year, and then our first variant of reverse iterative sampling reduced it significantly, but still it's nowhere close to leveraged scores, right? 24 hours. Not that practical. The fast reverse iterative sampling, now we're basically in the constant factor from computing leveraged scores, right? So that's pretty good. So that's essentially as efficient, but still that constant factor is there. For leveraged volume sampling, actually the dominant cost of the procedure is computing the leveraged scores. So I guess you could say that the improvement in the efficiency of volume sampling seems to be beating the Moore's law so far, and let's try to keep it going. Okay.
So is that the runtime after computing?
Yes.
After doing
There was after, yes, exactly, yes. So that's an important point. So you still have to compute the level scores. So that, yeah, that's the preprocessing step for everything. All of those methods require level scores.
Are you saying the first pop? I thought that there was like known poly time algorithms well before last
To
year.
approximate volume sampling. This is exactly.
So
Aren't there like these MCMC methods that like pretty much get it right?
right. So okay. So this is all for exact volume sampling.
And I guess that gives you the unbiased.
And also the terminology here is a little fuzzy. There's two variants of volume sampling. It depends on which subset size you choose. For the subset sizes at most, there was algorithm before then. For the subset sizes which we consider for linear regression, which is more than D, there was no algorithm until last year. So yeah, that's important to clarify. Okay, so we show that volume sampling is sort of like a natural distribution to look at. Now it appears to be quite fast to run, and it leads to those new unbiased estimators. And there's just a number of many open problems, one that I mentioned, and sort of questions related to it. So you get those unbiased estimators, but what if you want to introduce bias, like with this regularization, right? But you want to control that bias, right, so that you know what the bias is, unlike for leverage score sampling, for example. There's also the applications to distributed methods. And also, something I didn't mention is determinante point processes. Volume sampling, in some sense, is a determinante point process in a particular case, and the connections there are quite interesting. And here are the references that I mentioned throughout the talk. Thank you.
Any questions?
Is there a reason you didn't talk about the concentration bounds?
Right. That's a good question. So concentration bounds are natural for IAD sampling. Since volume sampling, you have this dependence, jointness.
Yeah.
That's sort of raises a challenge and makes it sort of less natural to look at concentration bounds. But in fact, you can show concentration bounds for volume sampling, which are for the leveraged volume sampling case that I mentioned, that the concentration bounds match the ones for leveraged score sampling, but so far we're not able to prove any better concentration bounds.
And this is the Perez-Pimentel paper?
No, actually. So well, that's also a good point. So what you're referring to is so there's this family of joint distributions which volume sampling does belong to, for which you can show concentration bounds, I guess negatively associated is the term, and so you can apply those, except in these tasks for sampling matrices, typically what you would like to have is matrix concentration guarantees, and those results do not transfer to matrix concentration guarantees. So that's like a big open problem, negative associativity concentration bounds for matrices.
I'll tell you more afterwards, because I've proved some that are coming out this year.
Oh, okay. That's very interesting. That's very interesting.
Okay, last one.
So regarding the case that your features, if your matrix is rank deficient, or in particular if your X, the data matrix, the design matrix, if there is significant decay in similar values, let's say. So can you do first a dimensionality reduction and then look at the volumes there? Like let's say you don't pick D vectors and look at the determinant of a D by D matrix. You look at a smaller, like a K samples and look at the determinants there. So is there any result that shows you what is the expectation of the loss if you just pick, let's say, the first K singular vectors and look at the determinant in data space?
I'm not sure. I mean, I know that there's results which say, okay, you have your high dimensional matrix, you sketch it, and then you do volume sampling or this kind of thing on it, and then you can say that to some degree this sampling approximates more or less accurately the sampling from the original matrix. Therefore, maybe it's worth using. But those are not very satisfactory because for this to work, the sketching has to preserve all of the determinants of all of subsets, which can be done, but it requires sort of more. It has bigger error bounds than what you would ideally like. So, so one direction towards that would be some kind of a variant of regularized volume sampling, which we started work on, but there's sort of there's a lot of sort of open directions for if the dimension D is large, that the current algorithms are not that efficient yet. So that's a sort of open direction.
Thank you again.